Now we are going to our last presentation of today. Eric Landahl from St. Paul University in Chicago will present his talk. Thank you very much, Eric, for coming here. And please load your presentation. Okay, good. Just expand it.
Thank you very much. You can hear me all right?
Yep, great.
It's a pleasure to get to talk today. This is a view looking south from our campus towards downtown Chicago. Out in this direction, about a 30-minute drive, is the Advanced Photon Source at the Argonne National Laboratory. I'll be talking about quite a bit of data taken there, as well as some experiments we've done at the Pohang Accelerator Laboratory in conjunction with my collaborator, Soo-Hyung Lee, who's at the Korean Research Institute of Standards and Science there. My agenda today is I'm going to start talking about, in general, the nonlinear lattice response of gallium arsenide to bulk photoexcitation, essentially how the lattice grows with increasing laser fluence. Then I'm going to talk about another recent experiment we published trying to determine a little bit more about the method of lattice expansion that's always seen by looking at the transport of charge carriers across a buried junction. And then finally, I'll talk about my main topic, which is some, I think, previously unpresented data on measuring very early phonon populations across the entire Bruin zone in gallium arsenide and germanium. So this is sort of what I had in mind when we designed the experiment to understand how any semiconductor would respond to photoexcitation, which was gallium arsenide in particular, because we knew it would exhibit many nonlinear properties like the elastic band shown here. And we wanted to trace out a curve where we would measure the extension or the lattice expansion based on the amount of laser light we put into it, and fully expected to see a linear region and a region that is not linear. And I'll show you how we did this, and that it comes from the presence of electrons. It's fairly standard at this point in time resolved X-ray diffraction setup. This data from the 7ID beamline at the Advanced Photon Source. So it's a 10 kilovolt synchrotron X-ray pulse, 100 picoseconds in duration, with an adjustable time delay from 100 femtosecond Ti-Sapphire 800 nanometer laser pulse on a perfect crystal of gallium arsenide at room temperature. And it's just a point detector, so we have really great angular resolution with this technique. And that becomes important when you try to view electron behaviors, which would be very fast, with a relatively slow machine that's taking snapshots at 100 picoseconds, as I'll explain. So as we increase the intensity and rock the crystal back and forth, we make these very fine rocking curves, which in this case shift to lower angles, implying, of course, a lattice expansion of the material. And then we plot out to just simply the centroid shift, say, giving us the average lattice expansion in femtometers via Bragg's law. And there's our curve that looks like the elastic band. You see at first there is at these lower bluer colors corresponding to 0.02 millijoules per square centimeter, fairly linear behavior. It then saturates, and at that point starts growing again. That's can be described by a bunch of purely optical absorption and electron model. So with increasing laser fluence going from left to right here, we first see single photon linear absorption. And then eventually, via the Burstein-Moss effect, a rearrangement, which happens probably very quickly, 2 picoseconds or less according to the literature, a depletion of free carriers in the conduction band. And that is what gives rise to the saturation effect. So to look at those first two panels here, here's a linear absorption due to single photons absorption. This is the profile against the crystal depth in microns and the carrier density ranging up to 10 to the 18 or so per cubic centimeter. That's initially created at the low fluence. As it's increased, the material becomes increasingly transparent due to the free carrier depletion, and the laser light simply penetrates longer. The probe depth with perfect crystals is given by the X-ray extinction depth, which is right about 1.5 microns. So we're essentially averaging over this area, and because it's a very smooth curve, we'll get back to that later, that means that the diffraction peaks that we observe are also very uniform and uniformly shifted, but not greatly broadened or distorted at first. As you continue to increase the laser fluence, here up to 10 times the initial value, something else starts to happen, which we ascribe to two-photon absorption and a increasingly non-uniform, shown here in the dashed green line, absorption of the laser light. To quantify the model a little bit, as you go to nonlinear strains in the mechanical system, you start to see some strange time behaviors. Shown here, you see with the elastic band, slowly the mass falling a little bit after it's actually put on. There it goes. And so it's generally, rather than just looking at a single time point, which would be the location of the maximum strain, what we showed in the previous slide was just shy of 1 nanosecond. Here we actually measure out the full set of dynamics at the different laser fluences going from low to high, and we find that the strain persists longer. It has a different recovery shape, and even the onset of some oscillations, which are also indication of non-uniformities perhaps starting to occur within the sample. Modeling this is done with a dynamic diffraction model that also includes charge density everywhere in the sample, including absorption effects, recombination effects, and diffusion. So we're quite confident that we can recapitulate it, but the point for today is that this is also caused by electrons. That is the electrons moving, which we directly view in these measurements. Here's an example of how you can then use that to engineer the strain in the material. So this is identical experiment to what I just showed, but using doped N-type gallium arsenide. So this is tellurium doped to 10 to the 18 per cubic centimeter, again, a bulk crystal at room temperature. It, of course, exhibits a much shallower optical absorption, about 100 nanometers in thick. And the result of that is you see multiple peaks when you start to have significant lattice shift. The X-ray penetration depth is probing both the unstrained substrate as well as the area closer to the surface, which is undergoing some distortion. At the beginning, the peak simply shifts linearly, and then at some point, there's the onset of saturation, where tracing that diffraction peak on the left, that is the one that's changing due to charge carrier expansion, we start, that comes on much earlier in the case of the doped gallium arsenide. And that would be because you expect electrons to be much more easily promoted from dopant levels to the conduction band. So effectively tuned the saturation point by doping in this case. And then again, with two-photon absorption onset, we see the expansion increase. And in fact, at high enough fluences, but still well below the damage threshold for gallium arsenide, one starts to see multiple orders come in. And these we interpret as being higher order photon absorption. So I think I've made the case that you can absolutely see, even with a slow probe, as long as recombination is slow and your spatial resolution is very high, it's only a couple of millidegrees across, implying femtometers of resolution, you can understand electronic processes by looking at high resolution diffraction patterns, even with lower time resolution. That's because essentially the electrons cause distortions which get frozen in place. Second topic I want to cover is sort of an extension of this, which is that if we can engineer the lattice strain, why don't we try making PN junction, or in this case, actually an IN junction, insulator N-type junction, which will actually separate charge carriers and let us to explore what exactly determines which species are contributing to the deformation potential. So the deformation potential, we have the electronic strain, is going to be proportional to the change in carrier density. Although which charge carriers there are, I think, at least up to this point, has remained unknown or maybe not thought about. And the deformation potential is either the derivative of the band gap with respect to applied pressure or the inverse of that number. And of course goes all the way back to the earliest days of trying to understand how band gaps change with pressure. And so that's phenomenologically is sort of the definition we use. And it was that constant that was used to convert strain into electron number in the previous modeling. So here we create a heterostructure. It's got a 30 nanometer N plus heavily doped cap with some electrodes on it. These are grounded. And laser light essentially goes straight through this, as shown in red, working at 400 nanometers and into a 500 nanometer thick AlGas alloy. And the AlGas is opaque, fairly opaque to the laser light. The X-rays continue to probe a depth through all of these into the bulk, which is again an N-doped gallium arsenide layer, which is quite thick, 350 microns or more, with again a grounded electrode on the back end. So following laser absorption, one would expect the creation of electrons and holes and for them to migrate around, and then charge separation to start to set in the sort of junction after a few nanoseconds, with the electrons crossing into the N-doped parts of the sample and the holes staying behind along with a few electrons. These vigorously will recombine because of the high combined density, generating lots of heat in the film layer, and the charge carriers, the electrons in this case, which pass into the N-doped sample, are going to be able to move quite a significant way through this region before they start to generate heat. This is what the data looks like. Again, there's the transparent, the transparent film on top. The transparent buffer on top is not shown. This is a absorbing at 400 nanometers film, and then the very thick bulk. And the high resolution diffraction techniques allow us to record actually on a logarithmic intensity scale, which is enough to completely solve the structure of the material. Its strain is a function of depth because of its high dynamic range. You can see interference fringes from the layers and the peak from the substrate as well as from the film. Here in time, this is in nanoseconds. So over the first few nanoseconds, we see, has been previously discussed, the rapid strain wave that comes from the sudden perturbation of the material. And so you see some wiggling of the strain waves as expected. But after that initial impulsive strain incident, interestingly, only the AlGas layer, shown here, undergoes modulation, whereas the substrate does not move significantly at all. And this is going out to a very long time delays, the point at which thermal diffusion would set in. This is actual plot of the strain taken from those peak shifts. We see at early times within a nanosecond sound wave propagation. It's been well studied. But then we see electronic and thermal strain. As mentioned, hard to tell them apart when you are only measuring the strain effects, but presumably resulting from both electrons and holes being present in the film, the AlGas layer. However, in the bulk, there is no modulation really whatsoever once that impulsive strain wave passes. And so we conclude from this, electronic strain does not transport across the interface along with the electrons. That's a rather strong claim. And to check it, there's a control built into the experiment, which is that those initial electrons created that pass through the junction will eventually generate heat deep in the bulk material. And that's evidence you can see in this first set of strain curves. So this is again the peak shift. This is a strain measured from the diffraction, and over the first 200 nanoseconds, this is the rapid transient as the impulsive strain goes. But then we're seeing heat being generated up here to 20 nanoseconds or so inside the film, and then it's starting to diffuse into the bulk material, which then correspondingly raises in temperature. But then something interesting happens, which is that at longer time scales, now here out to 3 microseconds or more, we've noticed this is a very robust effect that this substrate is warmer. And that is because those electrons have gone in, are heating very deep in, and the heat is actually moving back towards the junction and towards the surface, the area which is probed by the X-rays. So this indicates that we're not fooling ourselves. The electrons are in fact reaching into the bulk of the material. We just don't see their shift in their effect and strain until they have thermalized. So there's that the deformation potential seems to pretty much fail for electrons. And so we sort of conclude that the electrons must be somewhat invisible to a lot of the measurements that people are doing on diffraction. This is being followed up with several other measurements. We do know the electrons get there also because we can measure the voltage across the ends of our device and see what current actually travels. So electronic strain or the deformation potential appears to be species specific. All right, our final topic today is now that we're wondering about how exactly electron-phonon coupling works. Maybe it is that it's the electrons aren't participating so much in changing the valence binding, which is what holds the material together, and therefore the disappearance of those electrons, or that is the lack of them, the holes, is what actually is the thing that causes the lattice to expand rather than the electron physically being in the conduction band. So now we start to wonder, well, as we populate the conduction band in different places, what is this real effect on electron-phonon coupling? And so this was sort of a holy grail experiment which we'd wanted to do 20 years ago, but really was impossible until the advent of X-ray free electron lasers. So here's some new results where we actually try to see where is it that the electrons produce phonons in a measurable way throughout the Brouillon zone. This is now becoming a fairly standard diffuse scattering geometry. You work at grazing incidence, so the electron and laser beams match in penetration depth, and you take frames showing at different time delays what the scattering looks like across the Brouillon zone. I presume that here in the energy band level for the electrons, that depending on the excitation energy, shown in green, you're going to populate to different amounts, various different electron values after some electron normalization. And then the big question, and all we can measure, is actually where they go when they become phonons. So we don't measure the electrons directly, just like the other experiments, but only where they couple to phonons. And this data was collected at the Pohang Accelerator Laboratory, XFEL, in South Korea. We were very happy to be the first international users there when they turned on a couple of years ago. The first check is to look at static thermal diffuse scattering, where the phonons are simply populated by Bose-Einstein occupation numbers. Our experiment shows here at the center of 2 adjacent Brouillon zones under static conditions, the sorts of patterns that you would expect from theory from thermal occupation numbers at room temperature. Different distributions of phonons then will lead to different locations in terms of both angle and time as those distributions evolve, and therefore different locations lighting up in the diffraction or the diffuse scattering pattern. First check was done of the basic idea that we are in fact bringing electrons to different valleys. As we increase the laser energy from 800 nanometers to 500, we go and seem to have preferential filling of different values. And remember, this is measurements that come from looking at phonon population and not anything's known really about the electrons. But it does become clear here immediately, 2 picoseconds at least after excitation, that we populate the different values differently by choice of laser wavelength. When we look at the full dynamics, and I'll show these videos in a couple different formats. Here it is with the 2 adjacent gluon zones stacked on top of each other. For both gallium arsenide at a 500 nanometer pump, which is sufficient to go into many valleys, as well as the 800 nanometer pump for germanium, which gives a similar range of signals. A lot of interesting characteristics become apparent, particularly at the edge between the 2 zones, as you can say, for instance, see right here. This is just a raw data view of the subtracted images from the top. So the first gluon zone centered around this brightest dot here, and the second one over there. Then a lot of actions happening here along the line of symmetry between those two points. And the dynamics are tracked all the way out from the earliest times we can record at a couple picoseconds to thermalization. Let me show you then what the phonon distributions look like across the gluon zone of a bulk material at room temperature following photoexcitation. Here at 2 picoseconds, we see close to the zone center, of course, an enormous number of phonons, as you would expect down at the center. But then you start to see immediately halfway out, so at the zone edge, you start to see a substantial fraction of signal. And this is in both the gallium arsenide as well as in germanium. This is a time result plot, so you can sort of say this is a line out histogram as the time increases, going down. And there's quite a lot of interesting characteristics and signals, which again are very reproducible, but not completely explainable. And we have simulations underway. Eventually, you always get back to thermal distribution, of course. In that case, it takes about 350 picoseconds, and the gallium arsenide in particular is not cool, but now at a definable temperature. In this case, I think it is about 20 degrees above room temperature. Just a couple observations on this new data set. One is the large quantity of intensity that is shown here in between zones, which we believe is unobserved. Talk about the David Reese's group's measurement in bismuth in a moment, but they show different locations lighting up. At zone center is interesting because, of course, there's no group velocity in the dispersion curve for these phonons. They're stationary states, and they're populated at amazingly high efficiencies. Even when you take into account the different selection rules for polarizations of scattering, this is really, in this difference map, a very large amount of phonon flux comparable to what's at zone center, even at moderate, non-damaged fluences. So you have to start to ask, is this a built-in delay for thermal transport? Are we actually populating phonons at the zone edge very effectively, which then don't move very fast? And in fact, they do hang out in these experiments quite a while, waiting for some sort of anharmonic decay to happen. And that's observable in both materials. The Clements channel, or the filling in of the LA branch, sort of mid-zone, presumably from zone center, that was observed by David Reese's group in bismuth, is also seen in our data, but it happens a little bit later, about 30 to 40 picoseconds in the case of gallium arsenide. And so this long expected anharmonic decay channel, we also directly confirm via diffuse scattering measurements. Of course, we can't really say what the source of those phonons is, whether it's the zone edge or in fact from zone center. All we do again is view where they are, not where they're coming from. And just another couple points about the data. We see that gallium arsenide, being a polar semiconductor, has more decay channels, and indeed it cools faster. We see that at the same time, comparable overall effects, influences, that gallium arsenide really lights up entirely, say 150 picoseconds out across the entire zone line of symmetry, whereas there's still distinct hotspots. The zone centers are not connected yet. Phonons are not filled in all of those states. There are fewer channels in germanium, and it indeed cools much slower. With that, I'll end. Some future things are analysis of our fluence-dependent diffuse scattering, and looking at the thermal transport across the quantum zone.
Thank you very much, Eric. Excellent talk. Questions, please. Matthias, you raising your hand or you raising just? Okay.
Okay. Eric, very nice. I don't get the connection between the two parts of your talk. In the beginning, you showed nanosecond timescales, and I think the electron hole lifetime should be more on the few nanosecond and not 100 nanosecond. But maybe it's different in the certain material that you use. And then on the other hand, in your second talk, the phonons come out very quickly. And so is that the cooling of the electron hole pairs in the excited state? And then there's, for a couple of 100 nanoseconds, there's no additional creation of phonons? Is that what's happening?
Mm-hmm. So let me go back to those quickly at the beginning. So you asked about here why these long time scales and why it's a few nanoseconds. This is recombination and diffusion time, of course, but we have frozen in what happened to the lattice. The lattice only moves so fast. And so although recombination is certainly happening at this time, we're still seeing the effects of the electrons having been there, especially, of course, for the first nanosecond, because that's the speed of sound over that probe depth. So we're really seeing things moving out of the probe region at these early times. In terms of your
100 nanoseconds. You have 100 nanoseconds. The gallium arsenide is heated after 100 nanoseconds, or not?
But we move out of the probe depth very quickly. So although the heating is happening in this case quite slowly, the electrons are continuing to move. And thermal diffusion, of course, is very, very slow. So the electrons diffuse away quickly, or at least that would be our interpretation with this type of data. Mm-hmm. In fact, I think the electrons, especially at high excitation density, are usually believed to be supersonic.
Mm-hmm. Okay.
May I ask you a question?
Go ahead.
Did you try shorter pulses, taking into account the excitation depths and the refractive index? You can really go pretty thin layers, which we optically called it bleached layers on the top of the material. You showed on your bandgap pictures.
So you're saying could we have in the case of that, gone for shorter pulses and seen higher and higher?
Right, right. Because it's interesting effect around 10 femtoseconds with high refractive index material creating pretty much germanium, which, by the way, is a sample of that with refractive index 4. So you have a 10 femtosecond. It's pretty much below micron the depth of penetration. Yeah, like. Did you? No.
No, we did not. We did not vary the pulse duration in that case. No. Although I think would be a reasonable thing to check. Yeah.
Matthias, I don't understand. Do you raise a hand, or is it something behind your head, something yellow? Is it?
It's just plasmonic particles. Ask the other guys.
No. Something behind your head is something yellow. Looks like. Okay, it's not. Okay. So more questions, please.
Yeah, I do have a question. Maybe you partially answered to that already, but I don't know. So if you excite a different frequency, pump frequency, you do see different effects, right? Different
in the case of gallium arsenide, that's correct for the diffuse scattering. Yes.
Right. That's due to the fact that you are below or above the valleys of gallium arsenide, or is there something different playing a role? I mean, if you are below the valleys and you are only exciting near to gamma, I guess that the Froelich coupling is the dominating one. So zone edge polar phonons, zone center polar phonons. And if you excite into the valley, I guess you get more phonons involved. But this is what I would guess. Is this what your interpretation of your results?
That's my interpretation of this. Yes. Where it starts to not make sense, and I didn't show this data, is the dynamics also are very different. Subsequently, for these longer wavelengths where we're not as efficiently filling all of the valleys, and that we can't explain yet. The other data I showed on gallium arsenide was all taken at 500 nanometers, much higher than the gap.
Yeah. Okay. Yeah, we have a Mr. Vishal Shokin, please. Question.
Yeah, thank you for the talk. So my question is about slide number 16. Yes. So in the false color plot in the middle, I see that there are oscillations in the intensity for all of the Q modes for all. So do you know what is the origin for these oscillations, or are these true?
We haven't analyzed oscillation frequency. We don't have a lot of them. The configuration of this experiment was made to get as broad a region of reciprocal space at as high resolution as possible. And we did have fantastic temporal resolution in this very early run at the XFEL. So other groups frequently do look at what those frequencies are, and then try to match both the frequency and the wave vector with a particular phonon mode. And we have not done that, but you'll notice that these stripes are quite uniform all the way across.
Yes.
And that's definitely an interesting aspect of the data. And again, it's very repeatable.
Okay, thank you.
So thank you very much again, Eric, for excellent talk. I think we can extend the discussion offline. There is a time for now to adjourn the day session.